In this video, we're going to look at how we can use MATLAB to explore various Taylor polynomials for functions. So MATLAB can be able to generate those Taylor polynomials for a function. Okay, so as an example, let's take a look at this function, e to the x sine x, and let's consider it about the point x naught equals 0. We want to write MATLAB code to find 5th degree, 10th degree, and 15th degree Taylor polynomials. Okay, we're going to call them T5, T10, and T15, just to call them something, right? Then we're going to plot all four. We're going to plot the original function as well as the three Taylor polynomials from -2 to 2. We're going to use a legend. We're going to label it appropriately. And then finally, we're going to go ahead and take a look and see what can be said about the function and the Taylor polynomials as the order of the polynomial increases. All right, so I'm going to define sims to be f, T5, T10, and T15, just because I'm going to plot those, and I'm going to capitalize it because specifically it does say to call them capital T15, etc. And we know the function, and I'm going to call x to be a symbolic variable as well. F is going to be exp of x times sine of x. All right, now, and I'm going to suppress that because I don't need it. Now I'm going to get the Taylor polynomial. I'm going to call that T5. So T5 is going to be equal to Taylor of f. And then what we're going to do is we're going to use this call. It's going to be expansion point. Okay, so now be careful as you type it in. So you're going to use an apostrophe, capital E, and then lowercase expansion, and then capital P for point, okay, comma 0. Okay, so what that does is that it finds the Taylor polynomial about the point x equals 0, right? Now we have to tell it what degree. Okay, so I'm going to say apostrophe order. So here, we're going to have apostrophe order, and the order is going to be 5. Okay, now I'm going to suppress this, and then I'm just going to do an f print f. Okay, and I'm going to say that the Taylor polynomial, or the 5th degree Taylor polynomial, for %s is %s, and then /n. And I'm going to call first f, and then I'm going to call T5. Okay, now let me just run this, just so that way we can kind of see what's going on with this at this point. Okay, so I'm going to run this. Right. And it says the 5th degree Taylor polynomial for e to the x sine x is going to be x plus x squared plus x cubed over 3. Okay, now I can just copy this code. And what I could do is I could just change this to T10. And I'm going to change this to the order 10. And I have to change this to T10. And what will happen is when I run it, so now I get the 10th degree polynomial out of this, right? And then because it asked us to find the 15th degree, I'm going to do it one more time, copy and paste, and I'm going to find T15. So I'm just changing all the 10s now to 15. So this is T15, order 15, and then we're going to find the 15th degree polynomial. Now I should change, and I neglected to do this. This is the 10th and the 15th degree polynomial. Okay, so I just neglected to change them inside the f print f text. All right, we'll still get the right polynomial, but notice that we have two 5th degree polynomials, so it's just an error in what the f print f statement says. But regardless, we fixed it, and there we go. So now we have these Taylor polynomials centered about 0 for the various degrees of our polynomial. Okay, now what we can do is we can go ahead and plot these. Okay, so what I'm going to do now is I'm going to do easy plot. Okay. And I'm going to plot f from -2 to +2. I'm going to do a hold on. And I'm just going to easy plot now. And this time I'm going to plot T5. from -2 to +2. Right? And as you can imagine, we could just copy this code a few times. And I could just change this to T10 and T15. Now I'm going to hold off because I'm done. All right. And let me go ahead and run this just to show you. So we're going to get those 3 Taylor polynomials, which we already knew. All right. And I'm just going to expand this all the way. All right. And there we go. So it plots it on the same graph. Now, if you look at what was asked, we want to plot it, but we also want to use a legend to label the functions. Okay. So what I'm going to do is in order of how they appear. So we did F first, and then we plotted T5, then T10, T15. I'm going to use this legend function. And I'm going to have legend of F, comma, and then T5. Make sure they're in apostrophes, and then T10. And then finally, not surprisingly, T15. I'm going to title this y equals e to the x sine of x and various Taylor polynomials. And then finally, I can just go ahead and do my x label and my y label. So I'm going to say that this is going to be the x-axis, not the n-axis. All right, and then I'm going to have my y label, and that's going to be my y-axis. All right, so this should take care of part D, where we have to go through and plot and label, use a legend, and to make sure everything looks okay. So let me go ahead and execute this now. And just give it a moment. It's updating. Hopefully, there we go, finally. So we have the Taylor polynomials. Here's the legend of the colors, although we really can't see too much, okay? Because what's happening is, as the order increases, and we remember this from class, that the Taylor polynomials start to model the behavior of the original function, all right? And that's what's happening with this, okay? So the last part of the question is, what happens, or what can be said? I think I accidentally typed the sims into this Word document, but what can be said of the functions and the Taylor polynomial, or what can be said of the function and the Taylor polynomial as the order of the polynomial increases? What we can say is that we're going to f print f, and we can say as the order of the Taylor polynomial increases, the polynomial is a better approximation of the original function. And we'll use a /n, right? And this will be the last time we have to run this. All right, we're just waiting for this last one. So there we go. Probably should put lowercase increases, but not that it matters too much. Okay, so there we go. That's how we can use MATLAB to be able to not only find these Taylor polynomials, but also to graph and to compare them. And generally, the graph and the comparison to the original function can tell you if it's a decent model of the original function around those given points. Okay, so we can see that T5, like around -2, it's not really all that good of a model. And then similarly, as it starts getting like to 1.5, it's not that good of a model. Okay, so that's the whole purpose of graphing it, is that we can kind of see in an eye shot that it's pretty good about decently approximating the function from -1, probably up to like +1. And then after that, it starts to have a little bit more of deviant behavior from the original function. Okay, so that's it. Hopefully this is helpful for you all to be able to work through your MATLAB assignment.